In CSEC Multiple Choice Practice Paper 1A, we will take a look at the solution of the first 15 problems in CSEC Multiple Choice Practice Paper 1. The first one, how many kilograms are in 1 ton? The solution to this problem is very straightforward. That is, if you have accurate knowledge. So if you know, and as a matter of fact, all candidates of the CXC CSEC should know that 1,000 kilogram makes a ton. Knowing that 1,000 kilogram make a ton will cause the time to be spent on this problem to be equal only to the time that you take to shade in the answer. So if you know, you go straight ahead and shade in the correct answer. And as a matter of fact, that is the only time that this problem will consume. But what if you do not know? If you do not know for sure, you should at least think that it has to be some large figure, and begin by considering options C and D. If you do not know for sure that 1,000 kilograms make a ton, you should at least think that it is a large figure, and we will be thinking that option C or option D is correct. But how do we decide finally which one is correct? It is good to know also that outside of our regular metric table, milli, centi, of course, deci, hecto, all of those, outside of our regular matrix table, the most often used prefixes stand for multiples of 10 whose indices are divisible by 3. So outside of what we usually use in our regular table, outside of that, the power of 10 represented by the prefix is usually a multiple of 3, or we may say is divisible by 3. Therefore, we expect, for example, the prefixes to mean like 10 to the power of 3, 10 to the power of 6, 10 to the power of negative 6, 10 to the power of 9, 10 to the power of 15, 10 to the power of negative 12, those. So we expect that outside of our regular metric table, we expect the prefixes to stand for powers of 10 in which the indices are divisible or are multiples of 3. And the only one that fits this description is option C. So we think that option C is correct because here we have 3 zeros, which of course is equivalent to or is equal to 10 to the power of 3. And no problem, because we expect outside of our regular table the indices represented by the prefixes to be multiples of 3. Next, we need to write 3.14063 correct to 3 decimal places. And there we have a more magnified version of the number. And we are highlighting that it is to be written correct to 3 decimal places. Locate the third decimal place and that is located 3 digits to the right of the decimal point. 1, and we are continuing, 2, 3 places to the right of the decimal point, and that is our third place of decimal, and that is the one that we are concerned with. But in order to do that, we need the help of the decimal place of less significant. So check the digit that is next in order of significance. That is the one that is to the right. And why are we checking it? That is the one that we are investigating. The digit is a 6, greater than 5. Well, if it were equal to 5, the principle would have still been applicable. It is greater than 5. We therefore add 1 to 0. So we are going to add 1 to 0. The other digits are not affected by the operation. So after we have added the 1 to 0, the other digits of greater significance, those to the left, are not affected, and they are written exactly as they were before. So we have 3.141. Option B is correct. Let's move merrily on to another problem. Expressed in standard form, 0.00368 is equal to what? When writing a number in standard form, the number is increased or decreased by the number of decimal places required for it to have only one non-zero digit in front or to the left of the decimal point. So the decimal point has to be adjusted in such a way that we have one non-zero digit to its left. And such an adjustment may be to increase or decrease the original figure given to us by a particular power of 10. So we are going to be increasing or decreasing the number in order to make such an adjustment. Let's take a look at it. Of course, we have again a magnified version of the problem or the number that we are focusing on. Count the number of decimal places that the number is increased or decreased by in order to have only one non-zero digit in front of or to the left of it. That is, to the left of the decimal point. So we haven't moved yet, so that is 0. That is 0 because we haven't moved yet. But as we move now, we move for the first one, 1. For the second one, we move 2. And for the third one, we move 3. So we are adjusting the number in order that we only have one non-zero digit to the left of the decimal point, or we may say in front of, and some students may say in front of or before the decimal point. And there we have done it. The number is increased by 3 decimal places. This means that we have multiplied by 10 to the power of 3. And it is for you to appreciate that if we had the decimal point located here, and now we have it here, that the number that we had before is a lot smaller than the number that we have right now. And because it is smaller than the number that we have right now, it means that we have increased the original number by 3 decimal places, or by 10 to the power of 3. So we have multiplied that number by 10 to the power of 3 in order that we might have this appearance. Since we increase by 10 to the power of 3, we need to adjust what we have in order that it will be equal to what we had before. So we need to recover the original value of the number, and that is done by dividing by 10 to the power of 3. So in order that the decimal point may be placed right here, we have increased by 10 to the power of 3. So in order that we may recover the original value of the number, we will have to decrease by 10 to the power of 3, or we will divide by 10 to the power of 3. This equivalent is a multiplication by 10 to the power of negative 3. So we have increased by multiplying by 10 to the 3. To recover the original value, we will therefore multiply by 10 to the negative 3. And of course, there we have it. And these are leading zeros. And these leading zeros are not necessary to be included in the final answer. Of course, we have all our options right here, none of which has the leading zero. We may consider a number that initially has no non-zero digit to the left or in front of the decimal point as a small number. As a rule, we may say that numbers that are initially small should be accompanied by negative powers of 10 in the end. The difference between the number of decimal places in the initial statement and in the final answer will tell us the size of the power. So we could just do it like this in a very short period of time. So we are going to write this in standard form. So what do? We adjust this by 1, 2, 3 decimal places. So we know it's 10 to the power of 3 in the end. But because this number could be considered to be a small number, not having any non-zero digit to the left of the decimal point, then we know that the power of 10 accompanying the final answer has to be negative. So for small numbers, numbers that have no non-zero digit to the left of the decimal point, we are sure that those numbers are small numbers and must be accompanied by negative powers of 10. And the power of 10, or the value or the size of the power that we are considering, should be equal to the difference in number of decimal places that we have here and that we have in the final answer. So the number of decimal places by which we increase or decrease the number will give us the size. And of course, the sign of the answer is going to be dependent on whether we consider the initial number to be a large or a small number. So, write that number that we have there, 0.625, as a common fraction. Decimal fractions are all fractions whose denominators are powers of 10. The number of decimal places tells us the power of 10 concerned. So, do we have, very quickly, 1, 2, 3. So we have 3 decimal places. So the power of 10 will be 10 to the power of 3. So the number of decimal places is 3. The power of 10 that we divide by is 10 to the power of 3, which is equal to 1,000. The fraction is therefore the equivalent of 625 divided by 1,000. There we have it, 625 divided by 1,000, because we have what? 3 decimal places, so we have 3 zeros. Those 3 zeros signify that the decimal fraction that we have right here has 3 places of decimal. And of course, we will reduce this fraction to its lowest term. The fraction may be reduced by a common factor of 25. 625 divided by 25 is 25, and of course 1000 divided by 25 is 40. So there we have 40, and of course we are going to have 25. So 25 into 625 is actually equal to 25. We may have a further reduction by a common factor of 5. So we are reducing by 5 again. 5 into 40 is 8, and 5 into 25 is 5. Right, so our common fraction is 5/8. You may reduce the fraction in any way convenient to you. If you are more comfortable reducing the fraction by 5 each time, then do it. If you can see a reduction by 125, then there is no harm progressing in that manner. Lovely little problem that involves the manipulation of indices. Everything that is inside of the brackets will be affected by the power of 3. Everything inside of that bracket. So there we have the power of 3 outside of the bracket, showing that everything inside of that bracket will be affected by that power of 3. The coefficient, which is of course 2, is not inside of the brackets and will therefore not be affected by the power of 3. So there we have the 2, not inside of the bracket, not affected by the power of 3. It is going to be inside of the answer just as it is. Right there. And what do we know? According to the laws of indices, when we have a number with an index raised to another power, we multiply the indices. So we have inside of that bracket a to the power of 2, then it will be raised to the power of 3. So we multiply the indices according to the laws of indices, or the laws of the manipulation of indices. We will continue to apply the rule, but with the understanding that when the base is not accompanied by an index, the value of the index is 1. There we have it. The power of b is 1 because initially it was not accompanied by an index. So the value of the index is considered to be 1. So b to the power of 1 multiplied by 3, because when we have a power raised to another power, we multiply the indices. Then, by carrying out the multiplication process, the final answer may be written. So we are going to have 2a to the 2 times 3, which is 6, and b to the 1 times 3, which is 3. So we're going to have 2a to the power of 6, b to the power of 3. And that is represented by option B. A quadrilateral whose diagonals are perpendicular to each other but unequal is a... So the diagonals are perpendicular to each other but they are unequal. What is that one called? A quadrilateral with diagonals that are perpendicular but unequal is a rhombus. It is fine to know, but let us look at the reason for it. So there we have the correct answer, rhombus. There is your rhombus. It may be considered to be comprised of two identical isosceles triangles that are arranged with their bases in contact with each other. So let's see one isosceles triangle, two isosceles triangles. All sides of the rhombus are equal and they will be the equal sides of the isosceles triangle. So let us say this is your rhombus. Of course, we have all sides equal and we have an isosceles triangle here. So what makes this triangle isosceles is that this side is equal to this side, isosceles, and of course this one is also isosceles because this side is equal to this side for sure. Let us highlight the bases of the two triangles that are in contact with each other. So we are going to say that it's the base of each triangle that we have right here, just for convenience, right? Right. So let us highlight the bases of the two triangles that are in contact with each other. And it will be one of the diagonals of the rhombus. So there we have it. Right. So this is one of the diagonals of the rhombus, and those two triangles are in contact with each other by means of this common side of the two isosceles triangles. Let us now conveniently label two of the vertices of the rhombus A and B. So there we have vertex A, vertex B. Right. Recall the basis of the construction of a perpendicular bisector, and that you will find in Richard James Mathematics Resources. Of course, construct number 1, and that you will find in the instructional material. If we can locate 2 points, say C and D, in such a way that C is equal distance from A and B, and D is also equal distance from A and B, then the straight line through C and D will be the perpendicular bisector of AB. Remember that when we were constructing the perpendicular bisector, we said that if we can locate 2 points and the 2 points, each one is equal distance from A and B, okay, we can say that for the first one, and then also for the second one it is equal distance from A and B, then the line that goes through those 2 points will be the perpendicular bisector of A, B. And so we have these 2 points, C and D. Now, do not forget that this is an isosceles triangle, which is, of course, this is an isosceles triangle, which, of course, is a part of the rhombus. All sides of the rhombus are equal, and, of course, these are equal, which causes this triangle to be isosceles. So then, the distance from A to C is equal to the distance from B to C. Also, the distance from A to D is equal to the distance from B to D. Because of this fact, any line that goes from D to C will be the perpendicular bisector of AB. We have located 2 points, each one equal distance from A and B, which of course this is because of these two equal sides, and this one also is equal distance from A and B because of these two sides of the isosceles triangle. The equal sides of the rhombus causes C to be equal distance from A and B, and also D to be equal distance from A and B. The line through them is therefore the perpendicular bisector of AB. Right, therefore we are sure that this diagonal is perpendicular to this diagonal. So in a rhombus, the diagonals are always perpendicular to each other. The two diagonals are therefore perpendicular to each other but are not necessarily equal, because a rhombus is not necessarily a square. A square is definitely a rhombus, but a rhombus is not necessarily a square. And what is a rhombus? Any quadrilateral with all sides equal. That's a rhombus. And a square fits that description. Therefore, a square is a rhombus. Now, we will draw our rhombus a little bit flatter. So for this illustration, we have given the rhombus a flatter look in order to bring across our point. Of course, because it is flatter, one thing or what we imagine or intend to be obvious will be quite obvious. It is obvious that the diagonal AB is a lot shorter than the diagonal CD. Their difference in length is related to the fact that the angle DAC, the one that we have right here, DAC, this angle at the vertex A is not equal to the angle ACB, which is this one. So this angle is not equal to this one. They are different. The greater the difference between the two angles, the greater the difference in the lengths of the diagonals. So the greater the difference between the two angles, the greater the difference in the lengths of the diagonals. For a square, the diagonals will not be unequal in length. Why? Because all of the vertices of the square are equal. So for a square, the diagonals will be perpendicular and will also be equal. But the same is not necessarily true for a rhombus. So in a square, the diagonals are perpendicular to each other and they are also equal in length. That is for a square. There is always a problem in my mathematics resources that requires that students use a vector method to prove that a quadrilateral is a square. So we always have this problem. Show that a particular quadrilateral is a square. How do we do that? They need to show that all sides are equal. So in a square, all sides are equal. However, in a rhombus, all sides are equal also. So to finish proving that the quadrilateral is a square, they need to show that the diagonals are equal. So they need to also show that the diagonals are equal, because if it were just a rhombus that is not a square, the diagonals would not have been proven to be equal, or could not have been proven to be equal. For this particular problem, we need to find the intersection of the three sets that are given. And what do we mean by intersection? So the statement of the problem is soliciting the intersection of all three sets. The intersection of the three sets is the set of elements that are present in all three sets, or the set of elements common to the three sets. So they are present in all three sets. And of course we may say that the set of elements is common to the three sets. The element 2 is common to all three sets. As we can see, we have that 2 is in all three sets. There is no other element with that same characteristic under these circumstances. The correct answer is option B. Right. So option B, the set with a single element 2, that set is the set of elements that are present in P intersection Q intersection S. And of course, we know that it is common to all of those sets, P, Q, and S. Let us attempt to use a Venn diagram in order to solve the problem. But not without useful information and understanding. When inserting information into a Venn diagram, the elements of the intersection of all three sets go first. Right, so we have the element 2 is in all of those three sets. It goes first. There's nothing else to it because only the intersection of the three sets is needed. And we do not have another element to go into that intersection. And as a matter of fact, we do not need to continue to complete the Venn diagram because this problem requires only the intersection of the three sets. Which of the following relations is a function? Which one, if any, is a function? Well, if they are requiring that we identify the one that is a function, we imagine that one has to be a function. So let's proceed. A and B are not functions because the letter B in both domains is mapping to more than one element. So notice that B is mapping to 2 and 3 here. It is mapping to 2 and 3 here. So we are sure that A and B do not represent functions because this cannot happen in a function where one element is being mapped to two others. So let us strike those out. We are sure that those cannot be the correct answer. A is not a function for an additional reason that we will see in a few seconds. A is not a function, and we see the reason for that in a few seconds, and few short seconds, of course. In options A and D, there is an element in each domain that does not have an image. So C does not have an image and A does not have an image. Therefore, we are sure that A is not a function for more than one reasons, or we will say for more reasons than one. So A is not a function for more than one reasons, or we may say for more reasons than one. And of course, D is not a function because of that same reason that we are looking at. As a matter of fact, the reason that we are considering at this stage, that this does not map and this does not map. So we expect for a function that every element in the domain must map to another element, at least. So D is not a function and D is out, so we are only left with C. A function is a mapping from one set that is called the domain to another set that is called the codomain in such a way that an element in the first can only have one image in the second. Right? So that's what a function is. Each element in the first set can only map to one element in the second. That is a function. The only mapping that satisfies this requirement is option C. Although it has two elements mapping to the same element, it still maintains the principle that each element has only one image. So notice we have A and B, they are mapping to the same thing. But A is only mapping to 1 and B is only mapping to 1. Therefore, it is a function. And that is the correct answer. What property is applied when this that we have here doesn't matter? The details that we have is written as this. So, what is the property that is applied when this one is written as this? The expression is just a sum of 3 fractions. So that's what it is. It's just the sum of 3 fractions. And there we have them placed under the microscope. The sum of 3 fractions. However, in the first case, we have grouped the first 2, indicating that we will combine those 2 fractions, then add the third one to the result. So, that's what we mean. In the first case, we have these 2 grouped, as we have them right there. So it is still a sum, but these 2 are grouped. And this is indicating that in finding the sum of the 3 fractions, we want to combine these 2 first, then add this one to the result. In the second case, we have grouped the second and the third fractions, indicating that we will combine those 2 fractions, then add the first fraction to the result. So, there we have it. We have grouped these 2 in this particular case, indicating that we want to add these 2 first, then add this one to the result. It is a demonstration of the associative property of addition. It does not matter in which way we associate mentally or physically the numbers in a sum. The result will be the same. So if we are adding and we are associating these 2, and I'm using the word associate, of course highlighting that we are talking about the associativity principle. So we associate these 2 first, then we add this one, and of course in the previous case, like what we have right here, we are associating these 2 first, then we add this one to it. And of course, the result is still the same, and that's a demonstration of the associative law or principle. Option B is correct. If all of the operations were multiplication, then the associative law would have been applicable again. So, if we had multiplied, so if we have this fraction multiplied by this one, then multiplied by this one, then the associative principles could have been applied again. So we have the associative law applicable for multiplication and also applicable for addition. And as a matter of fact, when all of the signs are addition or all of the signs are multiplication, and you know, of course, if we have a mixture of signs, then we'll have a totally different ball game. Now, let us go back to the previous slide. There we are talking about commutative, distributive identity. So on the next slide, we will take a look at what those mean. So we have the order in which we multiply numbers does not affect the result. So if we say 5 multiplied by 2, that is equal to 10, or if we say 2 multiplied by 5, that is equal to 10. What principle is that? This is a demonstration of the commutative law. What about this one? There is no sign separating this D from the brackets. The operation that we assume is multiplication. we generally expand the bracket by multiplying D by A, then D by B. The letters in the resulting terms are written in alphabetical order in keeping with good mathematics manners. So we have D multiplied by A. It is the same thing as DA, but let us put the letters in alphabetical order. So D multiplied by A is DA, but putting them in alphabetical order, we have AD, then we have D multiplied by B, alphabetical order again, we have BD. This is an application of the distributive law that states that multiplication is distributive over addition. We see that the term that we are multiplying by, which is D, and of course it is the multiplier, it is distributed to each term in the sum by which it is being multiplied. So if we are taking this D and we are multiplying here, this D is distributed, and I'm using that word in keeping with the law that we are discussing, the distributive law. So D is distributed to each term. So the D will go with the A and the D will go to the B. So there we have D being distributed throughout the entire sum. And that is why we call that the distributive law. There we have it being distributed in the entire expression or throughout the entire expression. There we have 8 multiplied by 1 is equal to 8. This number is called the multiplicand, this the multiplier, and this is the product. When we form a product, the number that is being multiplied is called the multiplicand, and the one by which it is being multiplied is called the multiplier, and there is no doubt that the answer is called the product or the product. So what do we know? The multiplicand is identical to the product. This always occurs when the multiplier is equal to 1 and in no other case, with the exception of when the multiplicand is equal to 0. You know that if the multiplicand is equal to 0, 0 multiplied by any other number is going to be equal to 0. So in that special case also. But if we are speaking generally, the multiplicand is identical to the product when the multiplier is equal to 1. The property on display is identity, specifically multiplicative identity. So we are talking about the multiplicative identity, and that is what we are displaying here. Because the multiplier is 1, because the multiplier is 1, the multiplicand and the product are identically equal to each other. And of course, the property on display here is identity. An identity property may be shown for addition also when 0 is added to another number. The sum is equal to that same number. 0 is therefore the additive identity. So we have the multiplicative identity, which is 1. So when you multiply a number by 1, the result is the same number that you multiply by 1, as in this particular case. And when you add 0 to a number, the answer is equal or identically equal to that same number to which you are adding 0. So 0 is the additive identity. Now we have a very interesting problem. To which of the following sets belongs the square root of 25? What are the sets? Prime numbers, negative integers, positive integers. Let's investigate. When the square root of a number exists, it occurs in pairs. So the square root of 25 has a pair of answers if it exists. Of course, the square root of 25 exists. The square root of 25 is equal to positive 5 or negative 5. There is no problem seeing that when we square a positive 5, the answer is 25. No problem whatsoever. And there should be no problem also seeing that when we square a negative 5, we get 25. But we are going to put that under our proverbial microscope. And we see that negative 5 squared is equal to negative 5 multiplied by negative 5. So, that is what we have. Negative 5 squared is equal to negative 5 multiplied by negative 5. According to the laws of the manipulation of directed numbers, negative multiplied by negative gives a positive answer. So there we have a positive 25 with, of course, that plus sign before indicating that it is a positive 25. But we may write it as 25 because the value is positive with or without the positive sign. So, when we square a positive 5, we get a positive 25, and when we square a negative 5, we get a positive 25. Therefore, the square root of 25, we are sure, occurs in pair. The first one is positive 5 and the second one is a negative 5. So take a look at the options and the result of finding the square root of 25, and we see nothing but imminent danger, or we think that we'll have some danger. What do we have there? This is the result, positive 5, negative 5. And what do we have here for the options? We have prime numbers, the set of prime numbers, the set of negative integers, and we have the set of positive integers. So we are in for a showdown with the examiners, in which the examiners are convinced that their options are sufficient, and we are terrified that they may not have the correct option right there. So let us see which one is correct. So we do not have the option of a prime numbers, negative integers, positive integers. We do not have an option that includes all three of them. But let's see what happens. The answer is an element of each of the three sets of numbers. Right? So the answer is an element of each of the three sets of numbers. Of course, if it is positive 5, we know that positive 5 is a prime number, and we know that it is a positive integer. And if we are thinking negative 5, we know that it is a negative integer, or it is an element of the set of negative integers. So let's continue and see which option is correct. We are therefore sure that options A and B cannot be correct. So option A cannot be correct because we are sure that it is not 1 only, and we are sure that it cannot be 3 only. So those two options are out. We are with option C and option D. And of course, we still have here highlighted the sets of numbers, and the answer after finding the square root of 25. Although we are sure that options A, which is of course 1 only, and B, of course, which is 3 only, are incorrect. We are sure. The answer that we expect at first glance, that is not one of the options, cannot be correct either. We are sure that inside here we get all 3 sets. Right? We are sure that these numbers can be proven to be associated with all 3 sets. Therefore, we would imagine that we should have an option that caters for all of these 3 sets. Or is that so? At first glance, we expect the option that says 1, 2, and 3 to be the correct one. But it is not there. And rightly so. It is not there, and rightly so. So we are saying that, well, it is not there, and that is the one that we expect. But we are saying here now that it is correct not to be there. And let's see why. Why is it impossible for a number to be positive, negative, and prime all at the same time? Why? This is because the set of prime numbers is not a subset of the set of integers. It is a subset of the set of natural numbers. Natural numbers do not have negative elements, as do integers. Therefore, a prime number cannot be negative. Since a number cannot be both prime and negative at the same time, the option that says prime and positive, which is D, is the correct one. So of course, if we are putting in 1, which is prime numbers, as long as we are saying that it is a prime number, we have to imagine it is not 1 or 2 that we have here, and it is not 1 or 3 that we have here. We have 1 and we have 1 and. Therefore, we have 1, it is supposed to be a member of the prime numbers, and also a member of the negative integers. That is impossible because prime numbers are not negative. A prime cannot be negative, and the prime numbers are not stated with or accompanied by negative signs. Therefore, a prime number cannot be negative. Since a number cannot be both prime and negative at the same time, the option that says prime and positive, which is D, is the correct one. We are careful to say when the square root exists, because it does not exist in all cases. It does not exist all the time. The square root of a negative number does not exist at this level. So we have a negative 5. When we square that, we get a positive 25. When we square a positive 5, we get a positive 25. Therefore, there is no number that we can square to give a negative 25, confirming that the square root of a negative number does not exist. So the reason why we say when the square root exists, and we are careful to say that, is because the square root does not always exist. Because the square root of a negative number does not exist. As a matter of fact, if you take your calculator, insert a negative quantity, and try to find the square root of that negative quantity, you are sure to get an error. We may begin by placing the expression under the microscope. There we have the square of negative 3, and here we have the cube of negative 2. Right? And one of the great concerns in mathematics is the difference between the negative of a square and the square of a negative. So we are going to put that under the microscope. So where we have a negative 3 squared, here we have negative 3 multiplied by negative 3. That is what it is. Taking the numbers by pairs, the product of the negative 3's is positive. So the product of this is positive. Negative multiplied by negative is positive. We have it right there. And of course, what do we do next? The product of a pair of the negative 2's is positive. So we are going to take the pair. This 2, negative multiplied by negative again, is positive. And of course, we will have a single negative 2 remaining. There is an additional negative 2 that will cause the product of the 2's to be negative. So it will cause that product to end up being negative. So what do we do? 4 multiplied by negative 2 is negative 8. By the laws of the manipulation of directed numbers, consecutive positive and negative signs may be written as a negative. So when we have a pair of consecutive signs, if they are different, we will replace them with a single negative sign. So we will have 9 minus 8, and of course that is equal to 1. And our correct answer is 1, and that is represented by option C. Note that 4 is not added to 9 before multiplying by negative 2. In arithmetic operations, multiplication and division take precedence over addition and subtraction. So we do not say first 9 plus 4 is 13, then we multiply by negative 2. We do not do that, because in arithmetic operations, multiplication and division take precedence over addition and subtraction. So we will do the former first, and then we do the latter next. So we will multiply first, and then we add or subtract. So if we have a situation with a lot of multiplication, division, addition, subtraction, we will carry out the process of multiplying and dividing first, and then we will add and subtract, of course with the exception of operations that are enclosed in brackets, and those that are enclosed in brackets must always be carried out first. Taking a second look, we may take another approach to the solution of the problem. Whether a number is positive or negative, its square is always positive. A square is always positive. So when we square a number, whether it is positive or negative, the answer is always positive. What about the second one? When manipulating directed numbers, we learn that in a product or quotient, an odd number of negative signs will give a negative answer, while an even number of negative signs will give a positive answer. When we cube a number, we are actually multiplying it by itself 3 times. There will therefore be 3 negative signs, and of course 3 is an odd number, so we'll have an odd number of negative signs, and that will cause the result to be negative. The result will therefore be negative 8, so it is going to be negative 2 multiplied by negative 2 multiplied by negative 2, as we saw on the previous slide. And of course that will give us a negative 8, because when we are multiplying and we have an odd number of negative signs, that will cause the answer always to be negative. So we have 9 minus 8, which is equal to 1, and that's a very short way of arriving at our answer that we should opt for in a multiple choice paper. As a rule, any number, irrespective of its sign, raised to an even power results in a positive answer. Additionally, any number raised to an odd power results in an answer that has the same sign as the base. So if we had like a negative, if we had here like a 7, 9, 11, 21, we are sure that the result is going to be negative, because any number raised to an odd power will have the same sign as a number that we had before. So we have a negative 8 right there. So 9 minus 8 is equal to 1. Any number that is raised to an even power results in a positive answer, and any number raised to an odd power will have the same sign as the number that we have raised to that odd power. One method that may be used in converting a decimal, which is a base 10 number, which we have right here, to binary base 2, is to use repeated division by 2 and collect the remainder in the reverse order. So we will convert 16 base 10 to base 2 by using repeated division and by collecting the remainders in the reverse order. So there we have 2 into 16 will give 8, and the remainder is 0. Then we say 2 into 8 is 4, and the remainder is 0. We continue, 2 into 4 is 2, and the remainder is 0. Much the same or quite similar to what we do, but we do not use the remainders. When we are in primary school, we use tables like these for highest common factor and lowest common multiple, but we do not use the remainder section. As a matter of fact, when the number here is not divisible, we usually progress to the next step. But in this particular case, we are very careful to consider the remainders. So we are going to say again 2 into 2. 2 into 2 is 1, and remainder 0. And finally 2 into 1, 0, and remainder 1. What do we do next? The binary equivalent of decimal 16 is equal to the number represented by writing the remainders in the reverse order. So let us do that. So that goes first, of course, reverse order. And by the time we are through, we have the binary equivalent of 16 decimal, or 16 base 10. The correct answer is option B, the one that has the 4 zeros. 1, 2, 3, 4, right? So the one that has the 4 zeros, which is this one, is the correct answer. Let us do another one, but we will go to the next slide. Of course, might not be so obvious by using 16 alone what the entire process, the entire requirement is. We are going to throw in another number, and we are going to, of course, another base 10 number. We are going to convert that also to binary in order to make our statement a little bit clearer. So what do we do with 45? Same as before. 2 into 45 is 22, and the remainder is 1. Then we say 2 into 22 is 11, and the remainder is 0. Then, of course, 2 into 11 is 5. And the remainder is 1. Then we have 2 into 5 is 2. And the remainder is 1. Then we have 2 into 2 now. 1. And the remainder is 0. And then, finally, 2 into 1 is 0. Right. And the remainder is 1. Lovely. Let us use the same process as before with 45, which is collecting the remainders in the reverse order. Right. And that is how we finish our process of converting 45 decimal or decimal 45 to binary. This problem could have been solved by considering the analogy between the binary and decimal number systems. Let us take a look at how the place values are ordered in the binary system. So there we have our binary system, and those are our place values. Remember that when we are in the decimal, we have 10 to the power of 0 and all of that. Now we are in the binary, so we have 2 to the power of 0, 2 to the power of 1, all the way up to as many digits that are necessary. To convert 16 base 10 to binary, we look at the largest value in the powers of 2 that can be subtracted from 16. So we are using 16. So the largest one that can be subtracted from 16, the largest power of 2 that can be subtracted from 16 is actually 16. We therefore place the digit 1 in the appropriate place. So where we have 16, we place 1 right there. And that is the place value for 16. 16 minus 16 is equal to 0. So after we have placed the 16, we have no other value to place. No value whatsoever. All of the values are placed already. What more do you want? Therefore, the less significant places will be occupied by zeros. So those are the less significant places. We have, of course, power 2 to the power 4 is 16. So we have a 1 right here. So the lower powers of 2, we do not have any number for them. So we just complete the table by inserting zeros. There you have the binary equivalent of decimal 16. There we have it, just as before. This one followed by 4 zeros. And let us take a look at 45. We have our table, and we are taking a look at 45. What do we do first? Find the largest power of 2 that can be subtracted from 45. What is the largest power of 2 that can be subtracted from 45? 2 to the power of 5, which is equal to 32. So the value is 32. That is the largest one, 32. We therefore place the digit 1 in the appropriate place, right there. So we have a 32. 45 minus 32 is equal to 13. So we have 13 left. The largest power of 2 that can be subtracted from 13 is 8. The place value of 16 is therefore missing. So no 16 because we are at 13. So 16 is missing and we are at 8. So the largest power of 2 that can be subtracted from what is left, which is 13, is 8. The place value of 16 is therefore missing. It will be occupied by 0, and the place value of 8 will be occupied by 1. Right. And what do we do next? We take the 8 from 13, and we are left with 5. So that is what we keep doing all the time. we keep taking away the power of 2 from the remainder. So from 45, we take away the first one, which is 32. So from 45, we take away the first one, which is 32. We get 13. The next one we can subtract, because we cannot subtract the next one in line, which is 16. The next one that we subtract is 8. So when we subtract 8, we are left with 5. The largest power of 2 that can be subtracted from 5 is 4. The place value of 4 will be occupied by 1. So we occupy that with 1. And of course, what are we going to do next? We are going to subtract, because we have already accounted for the 4. So we are going to subtract the 4 from 5. That's what we are going to do next. So 5 subtract 4 is equal to 1. The largest power of 2 that can be subtracted from 1 is 1. The place value of 2 is therefore missing. It will be occupied by 0, and the place value of 1 will be occupied by 1. Right. There we have the binary equivalent of decimal 45, and it is of course equal to the same thing that we had before. There we have it. Right. There we have a reminder of the place values and the index form of the decimal number system. And of course we have used the binary number system just now, and we are showing that they are analogous to each other. So let us insert the number 500,329. So 500,329. And of course we see that some of the place values are not contributing any value to the overall number, but we have place holding zeros right there. Go back to 16 base 10, the one that is in the statement of the problem. A person who is very sharp on his binary may realize that 16 is the fourth power of 2. He may then write down 1 for that place value and include zeros for all subsequent powers. And of course, we're talking about the powers 2 to the power of 3 down to 2 to the power of 0. And because he's very sharp, he's identifying the answer in a few seconds. So, if you are sharp on your binary, you realize that 16 is 2 to the power of 4. So 2 to the power of 4, you put down 1 for that binary digit, and then after 16 is gone, there is no other number or no other value that can be included. So we'll therefore include place holding zeros. And of course, that will cause our problem to be solved, if we are sharp, in a matter of a few seconds. A boat is traveling on a bearing of 270 degrees. In what direction is it traveling? Oh, that's a knowledge problem. The answer to this question is dependent on your knowledge of the main directions that pertain to bearings and the angles associated with them. Let us take a look at them. North, east, south, west. Right. What are the angles associated with them? We have them right there. No problem seeing that. But we are focusing on the bearing of 270 degrees. Identify the direction that is associated with it, that is, with the 270 degrees. So we have the statement of the problem, 270 degrees. We have the direction, 270 degrees. And that is west. And that is option A. The heights in centimeters of 10 students are 150, and we have them all the way there. So we have all of them. And we are required to find the range of the heights. So what is the range? What do we mean by range? The range of a set of squares is the difference between the largest and the smallest. Let us first identify the largest item in the list. Where is that? 170. That is the largest item in the list. Cannot find the range unless we can identify the largest and the smallest, because the range is the difference between those two. So what do we do next? Let us identify the smallest item in the list also. 150. So what do we know? The range is equal to 170 minus 150, and that is equal to 20. The correct answer is option B. No problem with that whatsoever. Range is equal to largest minus smallest. We identify the largest, we identify the smallest, we find the difference between the two of them, that is 20. That's all there is to it. We need to find the area of the trapezium that we have right there. A trapezium is a quadrilateral with at least one pair of parallel sides. So we have our trapezium there with one pair of parallel sides. The area of a trapezium is given by, what does that mean? A is equal to B over 2 H1 plus H2. And as I've always told my students, when you get a formula, do not worry about the symbols that we have inside of the formula. Worry about the significance of the symbols that we have in the formula. Right? For all I know, we could have A here, B there, and C there. It does not matter what we have there, as long as they have the same meaning. So H1 and H2 are the two parallel sides. Does not matter what we have there, as long as they are the two parallel sides. And B is the perpendicular distance between the two parallel sides. So H1 and H2 are the two parallel sides, and B is the perpendicular distance between the two parallel sides. So those are the two parallel sides, H1 and H2. The two parallel sides, 8 and 12, they are going to go inside here. And the perpendicular distance between the two parallel sides, B, will go right there. So in this formula that we have right here, H1 and H2 being the two parallel sides that we have right here, we know inside here we will have 8 and 12 in any order. Addition is commutative. And of course we have B right here, which is the perpendicular distance between the two sides. So we have 3. So inside we have 8 plus 12, or 12 plus 8, and here we will have 3. Right. Now we simplify the arithmetic expression and we arrive at our answer. 8 plus 12, 20. And then what do we know? Common factor to reduce by, 2 here. 2 into 2 is 1 and 2 into 20 is 10. 3 times 10 is equal to 30. Option C. As long as you know the significance of the symbols that are used in finding the area of a trapezium, there is really no difficulty. So as long as you know the significance of the symbols in the formula, there's really no difficulty. And of course, the formula may be written without h's. We might not have any h at all, or we might not have any b here. But we know that the two numbers that we're going to have right inside here are the two parallel sides, and here we have the perpendicular distance between the two parallel sides. So there's no difficulty as long as you know what they mean. The only catch is the temptation to use the dimension of 5 centimeters in the place of b. The examiner probably imagined that candidates would just use any dimension without considering that it is the perpendicular one that is needed. They might have thought also that you would not be able to identify the perpendicular one. So the only catch, the only way that you can get this wrong is if you use these two as the parallel sides and then you jump to this one. Some students might not even know that they are required to put the two parallel sides in a formula like this. So the only catch that we imagine that will befall students is that they will not consider that it is the perpendicular distance between the two parallel sides that is needed, and they jump straight ahead and just use any one. But if you are considering the perpendicular distance, then this should help you to understand that we are talking about that this is perpendicular to this, and that is the significance of this. And of course, these two being parallel, then this one also has to be perpendicular to that one, and this of course is an indication of that fact.